I'm really glad to talk about our progress on optimizing AVI encoder today. We have long and close relationship with the AVI community because our co-founder Zoe Liu used to work with the Google video codec team from 2015 to 2018. She directly involved in AVI finalization and the implementation in libaom. So it's no surprise that we believe in the future of AVI since the very beginning of AVI finalization, and we have been working hard continuously to bring its power to the real world ever since. Visionular joined AOM as a promoter member, as the first member from the China market. And very recently, Tencent, one of the tech giants in China, joined AOM as a founding member. And also many other tech companies from China like Alibaba and more are joining AOM. That shows a growing interest and recognition towards AVI in the China market. And we are very proud to say that we have been contributing to that trend by actively participating in community events and promoting AVI to our customers and partners. AVI includes more than 70 coding tools and has the best coding efficiency compared to other codecs like popularly widely used in the world today, like H.265 and VP9, H.264. But the powerful coding tools also makes the encoder implementation very complex and especially challenging for real-world adaptation. Last year, released by MSU in its annual codec evaluation, that AVI encoder in libaom is 2,000 times slower than VP9. The number is astonishing. But it's arguable whether the experiment was set up completely fairly, and it's no doubt that libaom has improved dramatically after that, so the number should be much smaller now. But still, it's widely acknowledged that optimizing AVI encoder for real-world deployment is a challenging problem. So we come to solve this problem with decades of experience in video codec encoding and machine learning-focused innovation. In this talk, I'm going to show you our current progress in optimizing AVI encoder and share with you the ideas behind that. So before I talk about our own encoder, I'll briefly talk about the existing open source AVI encoders. You probably already know about this. libaom is the reference software for AVI, and it's generally known as with high coding efficiency, but also high complexity and really slow to encode. SVT-AVI jointly developed by Intel and Netflix. One of its most important features is to scale encoding to multiple threads, especially for cloud usage. It's making quick, fast progress in including major AVI coding tools. The Ravi is jointly developed by Mozilla, Ceph, and Vimeo. It aims to optimize the subjective video quality instead of objective metrics. And here I have a comparison of the different encoders with VMAF-based RD curves. It's published in May 2019, which may be already outdated now. But on the top, the best coding efficiency goes to libaom 2-pass. Then following that is SVT-AVI in green. Then the purple line after that is X265, followed by VP9 and X264. Decoder is very important to the ecosystem, of course, and David is a fast, scalable, and production-ready software decoder. You can decode 4K on mobile devices, as claimed, And more importantly, it's widely available on major browsers and also available in Android Q and Windows 10. With high performance decoder, software decoder, and wide availability, we are confident to say that AV1 is ready for wider adoption in real world. If we have an AV1 encoder that's fast enough and has good enough coding efficiency. And that's why we developed Aurora, our AV1 encoder that is ready for real-world adoption for video on demand and real-time communication use cases. For video on demand, we achieved better coding efficiency and faster encoding speed than X265 and in very slow mode and VP9. And for real-time encoding, we already launched to 2 customers this summer for lower resolutions like 480p. And for higher resolutions, we are making rapid progress and in the final stage of optimization. We expect to have that ready by early 2020. Before I talk about the numbers, I want to call out that although we compare to other AV1 encoders to complete the evaluation, our intention is not to compete with any AV1 vendors. Instead, we want to collaborate with everyone in the room and in the community to work together and advance the AV1 ecosystem and make AV1 a successful standard as a whole so that we all win. By making our encoder better and better, we contribute to this big picture and help to grow the community. All right, for VoD mode, we compare Aurora to X264 very slow and X265 very slow. It's done on a standard test sequence JCT-VC. We compare to X265 very slow because it's widely acknowledged as a benchmark for VoD. We also compare to X264 very slow because that's a popular existing solution among our customers, so they want to know the comparison. Compare with X264 very slow, we achieved more than 40% saving in both PSNR-based BD rate and VMAF-based BD rate. And compared to X265 very slow, we achieved around 20% for BD rate saving, and we are also more than 30% less in encoding time. So that's why we say our AV1 encoder is ready for real-world adoption for VoD. We also compared with libaom on a custom YouTube video set. Aurora in VoD mode has 2 speed settings, slow and fast. And because libaom is known for high coding efficiency and slow speed, so we choose the slow mode for our encoder to compare with. So on average, we achieved 10% saving in BD rate in PSNR. And also we achieve around 50% saving in encoding time. On this figure, each dot is a test video. The x-axis is the relative BD rate difference between Aurora and the libaom. One is below 0, it means Aurora is better in coding efficiency, and the left side is better. And the y-axis is the relative encoding time difference. When it's below 0, it means Aurora is faster than libaom. So you can see for most of the videos, they fall in the left bottom region, which means we are both faster and has higher coding efficiency. We also compare the rate control performance. In this figure, the x-axis is the different video clips, and the y-axis is bit rate. The blue line is the target. The two green lines are 5% above and below the target. The red line is libaom, and the yellow line is our encoder Aurora. So you can see we have much fewer overshoots than libaom, and we are mostly falling into 5% within the target. We also compared Aurora to VP9. On the same YouTube video set, for VP9 comparison, we used a fast mode of Aurora because VP9, compared to AV1, VP9 is less complex and runs faster, but with lower coding efficiency. So on average, we are saving 17% in BD rate in PSNR. And in terms of speed, we are on average saving about 4% in encoding time. So we are both faster and more efficient in encoding. That means if you are using VP9 in production today, you can switch to our AV1 encoder with gain in both encoding time and coding efficiency. We also compare to SVT-AVI. We did a test on a single machine with 8 cores and 16 virtual threads. We are aware that this might not be the perfect setup to test the performance of SVT-AVI if it's designed to scale to maybe hundreds of threads. And we admit that we are not as, in terms of multi-threading capability, our encoder is not as mature as SVT-AVI. But we start to prioritize now, so we are making fast progress. But we think this comparison is still relevant because not all the customers need or want the scalability to hundreds of machines. So compared to Aurora fast mode, compared to SVT-AVI, SVT-AVI also have different encoding modes with different speeds and coding efficiency from 0 to 8. So firstly, we compared, I have a typo here. It's actually Aurora slow to encode mode 1 because that's a slower mode for SVT-AVI. So for the slower setting, we're saving on average 18% in BD rate in PSNR. And for encoding time, we are on average saving over 90% in encoding time. Then compared to the faster mode of SVT-AVI with encode mode 4, we are saving about 27% in BD rate in PSNR, and also saving about 24% in encoding time. So in both modes, we are faster and has higher coding efficiency. Now I switch to talk about the real-time communication mode of Aurora. Here I show the RD curves comparing Aurora in real-time mode versus X264 medium. We choose X264 medium to compare to, again, is because our customers care about this comparison. So on the top is the PSNR-based RD curve, and the bottom is VMAP-based RD curve. The orange line is our encoder, and the green line is X264. So you can see we achieved significant gain over X264 across the board. And subjectively, maybe you can see the difference from left to right. On the small screen, I can clearly see there's more details with our encoder. I'm not sure if on the big screen you can see that. We also evaluated the rate control performance. On the left, the x-axis is different test sequences. The y-axis is the absolute relative difference from the target bitrate. The green line is, the blue line is X264. The orange line is Aurora. So we are maintaining the resulting bitrate mostly within the 10% of the target and more stable than X264. And on the right is the rate control result for one video clip over time. The blue line is X264, the orange line is the target, and the gray line is Aurora. You can see we obtain a more steady bit rate and follow the target better than X264. This is a snapshot of a demo we did by integrating Aurora in WebRTC. And we already launched Aurora real-time to 2 customers this summer. So to summarize, for VoD, we achieved better encoding time and better coding efficiency than X265. We are ready for real-world deployment. And for real-time, we already launched for lower resolutions and getting ready for higher resolutions very quickly. So now I'm going to talk about how we optimized our encoder with machine learning. So many researchers have extensively studied the opportunities combining machine learning with traditional signaling processing for video coding. For us, different from research problems, our biggest challenge usually lies in making the algorithm to run efficiently with real-life constraints, like CPU consumption or memory consumption or power consumption on mobile. So although I talk about our AVI encoder, but in real world, a video system involves more than just an encoder. Usually, what we care about is the end user experience. So frequently, it also involves pre-processing before the encoder and post-processing after the decoder. And at Visionular, we optimize all of those, include those in our solution as well. So in pre-processing, we modify the video frames before to make it more friendly for compression with minimal or without losing perceptual quality or even enhancing perceptual quality before the frame is fed into the encoder. For example, if we remove the high frequency details from the high frequency noise from the frame introduced by either camera or previous compression, it makes the video easier to compress because the higher frequency signals are removed. And it also can make the video more friendly for human watching. Maybe because like if the noise is properly removed, the image could be clearer, or sometimes when some details is removed from, anyway, so we found deep neural networks are really effective in removing structural noise, like compression artifacts. It can adapt to different video content and different noise level, which is especially useful for user-generated content. Another idea is to segment the frame to separate background and foreground or other regions that human eyes are sensitive to, like faces or text areas. Then we can separate the processing for these 2 types of regions to maybe remove fine details from the regions less interesting to human eyes, or we can feed the mask to the encoder to let the encoder adapt the compression level for different regions. For example, to use a higher compression level for the background or areas outside the face. And inside the encoder, there are many opportunities to use machine learning as well. For example, in bitrate control, the encoder needs to decide what's the best gulp structure, what's the best way to allocate the bits for each frame. And traditionally, it's done by hard-coded heuristics, which is suboptimal and not adaptive. So with machine learning, by training could be a simple neural network, taking the first pass statistics as input, and to predict the optimal rate control decisions. This can improve the coding efficiency and also making the encoder more adaptive to different video content because it's data-driven. Similarly, machine learning can be used for other decision-making inside the encoder, like partition mode decisions, coding tool selections, also in adaptive in-loop filtering. And then in post-processing, it's done after the decoder decodes the frame and before the frame is rendered to the user. Many topics has been extensively studied by the machine learning community, like super resolution, denoising, image enhancement, or multi-frame enhancement. They can benefit the encoding system because, for example, for super resolution, we can send a lower resolution video over the wire and then boost up the resolution after decoding. Lots of bits can be saved. But like I said, our biggest challenge is to make the algorithm fast enough and efficient enough to run maybe real time on mobile devices. And we have done lots of exploration for that. Currently, we can do 30 FPS at 720p on iOS devices and high-end Android phones. Here's an example from our super resolution post-processing. Another example for this can be both pre-processing or post-processing for SDR to HDR. Here's a quick glance over our involvement with different events globally to promote AVI. So we're really glad that our progress in AVI encoder optimization has been well received, and we look forward to working with everyone in the community to further push AVI forward for wider adoption.
Time for a couple of quick questions, Alex.
The real-time part of your presentation. My question will be about the real-time part of your presentation. In June, Cisco presented an AVI implementation in WebRTC in WebEx with, I think, 720p or 1080p. Thomas, you will correct me if I say something wrong. On a MacBook Pro, you only do 480p and you only compare with H.264, or would that compare with the demo and the number that were provided then? I think they implemented a non-compliant AVI in RTP payload for WebRTC at that time with no SVC support but real time, correct?
Yes, it's compliant with the RTP payload spec, and
But no SVC.
There was no SVC, no.
So how does your AVI implementation in WebRTC and your encoder speed compare to that or to the real-time libaom implementation?
We haven't looked into that. It's definitely worth looking at. Yeah, I'll check the numbers and maybe do more experiments.
And why only for ATP?
What's that?
Why only for ATP? It was reported 10 ATP real time on a MacBook Pro, correct?
The experiments might be done under different constraints. For our experiment, we are only using 2 threads on a moderate desktop computer. And the reason behind that is some of our customers don't want the CPU load to exceed, say, 25% or 30% of a single machine at a time. So I need to check the details of their setup.
Thank you.
Thank you.
Okay, one last question, quick one.
Okay, thanks for the presentation. It's very impressive. Can you go back to one of the slides showing the encoding, decoding, post-processing? Yeah, can you just briefly highlight how much percentage is pre-processing or post-processing brings in encoding time and the performance gains? Pre-processing and post-processing, like how much gain or time complexity does it bring on top of the encoder itself?
I don't have a simple answer to that because we don't use all of these tools at once for every customer. We actually customize based on their need and their user scenario. So they don't really need all of this for their use case. So, but say, for example, with neural network-based denoising or enhancement in pre-processing, we're seeing maybe 5 to 10% in terms of BD rate in BMAF. Another thing is, say, for example, with region of interest-based pre-processing or encoding, it's hard to evaluate with objective metrics, even with BMAF. So it's hard to say. But,
Okay, thank you very much.
Thank you.